A mysterious streak outpaced the stars above Mars. In October 2025, cameras on the Perseverance rover snapped a surprising flash zipping at 60 kilometers per second, aligning perfectly with the velocity and schedule of the interstellar object 3I/Atlas during its groundbreaking flyby of the Red Planet. Planned orbital spacecraft suddenly lost signal, and the unedited photos disappeared into obscurity. Soon, unverified accounts of several swift bodies and an enigmatic green glow emerged, leaving astronomers tense with anticipation. Initial flyby snapshots suggested irregularities, actions unlike those of any typical comet, and official disclosures halted right when clarity was crucial. What secrets lie in those absent shots? Might these hints upend our understanding of objects from beyond our solar system? On October 2, 2025, Stephen Burns, a prominent name in amateur stargazing circles, shared a 9-minute time-lapse of the Martian night sky, pulled from Perseverance's raw image library. Compiled from a series of back-to-back exposures, the footage reveals a sharp, slender line slicing through the starry Martian backdrop. The evident speed of 60 kilometers per second grabs attention right away, surpassing speeds of familiar meteors, orbiting satellites, or usual cosmic ray marks found in rover footage. By way of reference, NASA's Parker Solar Probe, humanity's quickest creation, hits 192 kilometers per second, but only near its closest solar approach, fueled by the sun's gravitational pull. In this instance, the line maintains a consistent velocity at Mars's range from the sun, a rate generally linked to travelers from interstellar space. Burns employs a precise approach. He aligns the unprocessed images over a stable star directory, adjusts the scale via established stellar distances, and verifies timing across each frame. The line's path gets tracked against stationary stars sequentially, eliminating possibilities of stationary lens flaws or radiation strikes. After fixing missing frames and verifying against accessible celestial maps, he releases the complete dataset and encourages fellow enthusiasts to verify or debunk it. The outcome sparks a massive online buzz. Thousands grab the images, reprocess the composites, and argue if the line is genuine, a glitch, or an even odder occurrence. Burns's track record for analytical depth and caution lends credibility to his reveal. He stresses the importance of outside verification, cautioning against wild theories until the line's source gets solidly corroborated. The math checks out. Should the 60 kilometers per second figure prove accurate, the trajectory aligns spot on with the forecasted path of 3I/Atlas across the sky. Yet the onus now falls to the wider group. Hobbyists jump at the opportunity. Will others confirm the oddity, or will it fade under rigorous examination? Discussion boards explode the moment Burns's video drops. In mere hours, countless solo researchers snag the Perseverance data, keen to echo or refute the 60 kilometers per second trace. Opinions split fast. A few achieve results. Using tailored algorithms to layer the shots, they not only detect the primary path, but also subtle signs of additional rapid entities in the October 3 data. Counterparts employing different methods detect only static. Charges of data manipulation and glitch-chasing ping between sides. Around 0003 UTC, a short emerald burst shows up in one team's rendered sequence. This low-res anomaly ignites a flurry of guesses. Does it mark a true light burst, or merely a radiation impact boosted by intensive processing? Competing groups probe the hue layers, clashing on adjustments and lens configs. Proponents argue the green glow fits comet chemistry, like a spectral emission. Skeptics rebut that the planet's sparse air and the imager's hardware traits render such bursts more prone to sensor echoes than actual events. The scarcity of pristine, untouched files heightens the doubt. Lacking the source fits data and sensor logs, all assertions remain tentative. Metrics on signal strength, sequence stability, and ray filtering turn into contention zones. No prompt data rollout, no quick processing batch, no adjustment tools stokes doubts further. Is this standard delay for dynamic observation efforts, or a calculated holdback? Irritation builds among participants. Certain voices call for agency intervention, pressing NASA or ESA to intervene and resolve the debates. Others intensify collaborative efforts, uploading scripts and partial assemblies to foster group-backed proof. The trace's authenticity remains suspended, its future hinging on if forthcoming orbiter operations yield clear, separately confirmed visuals. For a fleeting period in early October, Mars served as the prime solar system observatory for an interstellar intruder. 3 satellites, MRO equipped with HiRISE, ESA's Trace Gas Orbiter with CASIS, and Mars Express with VMC, were assigned to image it at 3.9 million kilometers away. That's roughly 75 times Earth's lunar separation. Such an immense gap means even Mars's keenest lens, HiRISE, would render the visitor as barely more than a blur. Its optimal clarity would barely instruments like HiRISE, which typically resolve details down to dozens of meters per pixel on Martian terrain, weren't designed for chasing something hurtling along at such velocities or distances. Engineered to detect rocks on rugged hillsides, it had to be retargeted for this high-speed pass, with its capture routines adjusted using fresh orbital data to direct the tight viewing angle just ahead of the forecasted route. Every shot was a risky bet. Fire too soon, and the target slips out of the frame. Wait too much, and it blends into the starry backdrop. CASIS, optimized for colorful shots and outbursts, lined up a sequence of 4 filter images, aiming to snag not only the core, but also any debris or streams lagging in its wake. The HRSC on Mars Express, with its broad sweep and multiple wavelengths, took on the job of picking out basic outlines. Would it tell a lone core apart from a swarm, or pick out a solar-directed burst amid the brightness? The whole effort demanded flawless teamwork. Observation schedules for each satellite hinged on spot-on forecasts from JPL's Horizon system, refreshed every day as the path of C/2019 Y4 Atlas sharpened. The probes had to pivot from their standard nadir orientations, occasionally by a few degrees, to follow that tiny dot across the vast cosmos. Onboard constraints ruled out live following. Each photo relied on the precision of final-hour computations. For something so distant in the solar system, a small glitch in the orbital info could spell complete failure. As the encounter neared, the sensor groups balanced clashing demands, stretching out imaging durations, cutting down on radiation interference, and carving out bandwidth for swift data transmission. Each picture faced intense examination for signs of form. Was C/2019 Y4 Atlas one firm chunk, a scattered pile of pieces, or an even weirder setup? From this vantage, only traits spanning tens of kilometers would show up. If the color filters worked, they could expose material clues, wide bands of green, blue, or red suggesting unusual makeup. The pressure was immense. Ground telescopes on Earth were washed out by the sun's light, leaving Mars satellites as the sole sharp observers. The goal was straightforward. If unusual activity kicked in, splitting apart, spurts, sidekicks, these shots would reveal it first. The operation boiled down to outrunning the angles, speed, and clock. No unprocessed photos. That's the line repeating in every chat as the hours pass post-Mars encounter. Usually, data from Mars satellites, particularly from big moments, floods open databases in days after receipt, even if raw. Here, zero output. Nothing from HiRISE, nothing from CASIS, not even the standard preview shots from Mars Express. The quiet is total, interrupted just by mission reports alluding to continuing adjustments and checks. At JPL, the photo specialists deal with another layer of stress. The issue goes beyond data flow or red tape. It's the danger of dropping images peppered with radiation specks, unflagged bad pixels, or jumbled layers that might pass for actual debris or sprays. For a fast traverser like C/2019 Y4 Atlas, racing at 60 kilometers per second, usual processing chains falter. Background leveling, shape fixes, and light measurements all need overhauls. Even top-tier radiation removal tools, set for sluggish Martian vistas, falter at sorting true cosmic trails from random ions. JPL's photo chief, under the glare of outside eyes, calls the effort a sprint to beat mistakes and hopes. Each image gets probed for alignment shifts. Did the orbital forecast match the real heavens? Did a radiation zap or sunflake create a brief mark mimicking a side body? In this setup, even layering photos, a basic task, turns hazardous. Off by a sliver, and fakes proliferate. Push the merge too hard, and subtle true details fade. The risks are obvious. Drop them hastily, and a false blip sparks worldwide hype. Drag it out, and whispers of hiding grow. The adjustment crew advances photo by photo, matching expected movement to real pixel paths, marking weird spots for hands-on inspection. Each potential chunk, each strange glimmer, ends up recorded, discussed, and either dismissed or flagged higher. Nobody at JPL pretends the holdup feels good. Truth is, it's a jam of carefulness, favoring accuracy over haste. While the public hangs in suspense, the upcoming drop must do more than feed interest. It has to prove, through proof, if Mars lenses nabbed one core, a debris group, or whatever calls for a fresh take. A comet's emerald shine, spotted from millions of kilometers out, is normally a slam dunk. Dicarbon, or C2, gives off a vivid green mark when solar rays snap its ties, a method so steady that seekers treat it as a signature tag. For C/2019 Y4, Atlas, though, things complicate. Accounts from during the Mars close approach period, observers spotted a brief emerald glimmer at 0003 UTC within certain Perseverance image sequences. The conclusion drawn is straightforward. Should this glimmer prove authentic, it would indicate the presence and activity of dicarbon in the comet's atmosphere. Yet initial tentative analyses from Mars Express and the Trace Gas Orbiter suggest otherwise. The anticipated C2 emission features appear faint or entirely absent, supplanted by a gaseous composition heavy in carbon dioxide and scarce in traditional carbon molecules. In laboratory contexts, an emerald glow devoid of dicarbon represents an impossibility. Conventional astrophysical explanations struggle to account for a greenish spectrum missing the characteristic swan bands around 516 and 563 nanometers. Assuming the hue is legitimate, it calls for an alternative process or an unidentified substance influencing the outcome. Experts in spectroscopy, accustomed to debunking misleading signals, recommend restraint. Absent precisely synchronized, calibrated spectra aligned with the flash's timing, this chemical inconsistency stays unexamined. Could the emerald have been a true radiative occurrence, or merely a glitch from image processing and enhancement? Only the release of unprocessed data from Mars satellites can clarify this discrepancy, demanding instrument-confirmed spectral readings. Upcoming data drops must demonstrate, at the pixel level, whether 3I/losses composition truly defies established norms. Observations from the Mars mission challenge foundational principles of cometary studies. Preliminary findings from the Mars Express group emphasize a spectral signature led by nickel emissions rather than iron, inverting patterns seen in typical solar system comets. Normally subdued nickel features now dominate, overshadowing iron lines. Researchers scrutinizing elemental proportions observe that no conventional accretion theories foresee this dominance hierarchy. The irregularities extend beyond heavy elements. The Trace Gas Orbiter's sensors detect a gas profile where CO2 release vastly exceeds water vapor by a factor of 10. For a body warming as it nears the sun, H2O should prevail in such scenarios. Here, CO2 reigns supreme, with water barely detectable. The ejection patterns add further intrigue. Imagery from Mars orbiters, despite resolution constraints, reveals a jet stream not streaming sunward but propelled ahead, an anti-tail, sunward pointing, and distinctly edged. This stream drops off so abruptly that dust simulations fail to replicate it adequately. The usual expansive, fan-like tail is nowhere to be found. Rather, the jet's forefront sharpens intensely, with an improbably abrupt decline in luminosity. Simulation experts project that sustaining such a feature would require a nucleus of immense size and density to avoid fragmentation or trajectory disruption. Monitoring groups assess the body's mass via deviations from pure gravitational motion, subtle pushes from asymmetric gas releases, or jets. For 3 SUNY/Atlas observations, results show no deviation. Despite evident outbursts, its trajectory adheres closely to the forecasted orbital path. This suggests a minimum mass exceeding 10 billion tons, more akin to an asteroid than a comet. Investigators document, discuss, and compile each peculiarity into an expanding file of evidence. Conventional theories strain to accommodate the compositional quirks, the kinematic behaviors, and the formidable bulk. Tension builds as astronomers debate if these traits merely revise cometary paradigms or hint at something beyond natural origins. Flyby, renowned for challenging frontiers in interstellar studies, contributes a bold assessment. His colleagues execute trajectory simulations, retracing 3I/Loss's course over years to check for alignment with the iconic 1977 WOW signal. That 72-second radio pulse at 1,420 MHz, the neutral hydrogen frequency. Employing JPL Horizon's data and Monte Carlo methods, they pegged the probability of this positional match at roughly 0.6%. Uncommon, yet feasible. The hydrogen line carries profound significance in SETI communities as the prime candidate for extraterrestrial transmissions. Flyby's team contends that an interstellar traveler crossing the WOW sky region warrants dedicated radio scrutiny. SETI specialists, ever prudent, highlight risks like location ambiguities, cosmic scale, and hindsight bias. Nonetheless, the precision of a narrowband hydrogen emission endures as the benchmark for non-natural origins. Nature avoids such focused broadcasts. With 3Pond/TLOS now solar concealed, uncertainty persists. Might the upcoming radio opportunity yield more than quiet? Post-October 29th, 3I/LOS enters solar occultation, creating a tracking void for terrestrial and Martian telescopes alike. Over the ensuing 5 weeks, no observatory can monitor its whereabouts, luminosity, or morphological changes. Such interruptions are routine around perihelion, imposed by solar interference and orbital safeguards for probes. Through November, experts in planetary science, backyard stargazers, and technosignature seekers alike monitor the timeline, anticipating mid-December's return in the morning heavens. For essential observables await evaluation. Key factors will dominate the monitoring agenda: total luminosity, path relative to fixed stars, coma or ejection patterns, and emission signatures. All these aspects will undergo close examination for alterations. Has the entity broken apart, dimmed, or altered its direction? The upcoming observation period is short yet crucial. Confirmation hinges on whatever appears after passing behind the sun, and if the observations align with forecasts or intensify the enigma. Distinguishing authentic signals from interference starts with a straightforward hierarchy. At the foundation, consistency across observations. Legitimate traits, such as trails, bursts, or satellites, ought to recur in separate image sets, aligned by timestamps and orbital data from various groups. False positives, however, disappear with adjustments to processing or instrument tuning. Following that, validation across wavelengths. A legitimate body should show up in multiple bands or spectra, displaying color indices that align with known physics. Spurious effects typically appear only in one filter or alter hues with varied analysis. Higher up, positional and kinematic signatures. Authentic escorts should travel in tandem, following forecast orbits while keeping steady distances, without sudden leaps or distortions tied to imaging sequences. The pinnacle involves intentional maneuvers or features like purposeful shifts, targeted radio emissions, or recurrent patterns. These define natural explanations. Every assertion ascends this framework, encountering stricter scrutiny at each level. The evidentiary threshold escalates with the boldness of the hypothesis. The tally remains public. Flag each irregularity, require substantiation, and allow the facts to decide. Chemically anomalous. I/Atlas defies standard comet profiles. Its iron-to-nickel proportion, dominance of carbon dioxide, and enormous solar-directed jet all deviate sharply. Still, the pivotal proof stays concealed from scrutiny. The trajectory forecast intersects the site of the 1977 WOW signal at an estimated 0.6% chance, though no separate radio observations have surfaced. As I/Atlas nears its closest solar approach amid an observational blackout, scrutiny calls for caution and precision. Pending the following data drop, the riddle persists. We're left with a cosmic conundrum, layers of oddities, and zero verified resolutions. Just the observations and our subsequent actions.